you for that fantastic introduction. And hi, I'm Lynne Clark, and I make code cartoons. And I also work at Mozilla on things like WebAssembly, which is what we'll be talking about today. And I'm joined by Schneidereit, who leads our WebAssembly tooling efforts, and will be filling us in on some of the work that they're all doing. So first off, what is WebAssembly? WebAssembly is a way of running programming languages other than JavaScript on the web. Up until now, to run code on a web page, the only language that you could use was JavaScript. But now that there's WebAssembly, you can use other languages, like Rust and C and C++. Now, I've noticed that some people have a misconception about WebAssembly. They think that the MVP that was turned on by default in browsers in 2017 is the final version of WebAssembly, and I can understand where that misconception comes from. The WebAssembly community group is really committed to backwards compatibility, so that means that the WebAssembly that you write today is going to continue to work long into the future. But that doesn't mean that this WebAssembly is feature complete, and in fact, that's far from the case. Features are coming to WebAssembly which will fundamentally alter what you can do with WebAssembly. I think of these future features kind of like the skill tree in a video game. We've fully filled in the top few of these skills, but there's still this whole skill tree underneath that we need to fill in to unlock all of the applications. So let's look at what's been filled in already, and then we can see what's yet to come. WebAssembly's story starts with Emscripten, which made it possible to bring large existing C++ code bases for things like games and desktop applications to the web. And it did this by transpiling that code to JavaScript. Now, at first, this JavaScript was slow, but then there was a Firefox engineer who saw that you could add an optimization to the engine to make it run fast. And this gave us ASM.js. Once the browser vendors, all of the browser vendors saw how fast ASM.js was, they started adding the same optimizations to their engines. But this wasn't the end of the story, it was just the beginning of the story. Engines could still make this faster, but they couldn't do it in JavaScript itself. Instead, they needed a new language, one that was designed specifically to be compiled to. And that was WebAssembly. So what skills were needed for the MVP, running C and C++ on the web? Well, WebAssembly's designers knew they wanted to support languages besides just C and C++, so they needed a language-agnostic compile target. Something like the assembly language that things like desktop applications are compiled to, like x86. But this assembly language wouldn't be for an actual physical machine, it would be for a conceptual machine. Now, this compile target also had to run very fast to meet users' expectations for smooth interactions and gameplay. And it also needed to load fast, because the web's users are used to fast load times. But these kinds of applications are pretty large code bases, which means that there's a lot to download and compile when the user first goes to the URL. So we needed our compile target to be compact, and that way I could go over the internet quickly. These languages also needed to use memory differently from JavaScript. They needed to be able to directly manage their memory. This is because languages like C and C++ have a low-level feature called pointers. And pointers need to be able to write to and read from particular memory addresses. But you can't have a program that you downloaded from the web just accessing bytes on your computer willy-nilly. In order to provide a way to access memory directly like a native program is used to, but keep the browser secure at the same time, we had to create something that could give access to a very specific part of memory and nothing else. To do this, WebAssembly uses a linear memory model. And this is implemented using something called typed arrays. So this is basically just a JavaScript array, but the only thing that it can have inside of it is bytes. And this means that when you're accessing it, you're just using array indexes, which you can treat as though they were memory addresses. And this means that you can pretend that this array is C++ memory. So with all of these things in place, you can run desktop applications for things like games in your browser as if they were running natively on your computer. And that was pretty much it for the skill set that WebAssembly had when it was first released as an MVP. It truly was an MVP, a minimum viable product. It allowed certain kinds of applications to work, but there's still a whole host of others to unlock. So the next achievement to unlock is heavier weight desktop applications. Can you imagine if something like Photoshop were running on the web? You know, if you could use it like use it Gmail, where you just go to the website on any device, and you can immediately start interacting with things. And we've already started seeing things like this. So for example, the AutoCAD team has made their CAD software available through the browser. And Adobe has made Lightroom available through the browser using WebAssembly as well. But there are still a few features that we need to make sure that all these applications, even the heaviest of heavyweight applications, run well in the browser. So first is support for multi-threading. Modern-day computers have multiple cores that can process things in parallel. But to make use of these cores, you need support for threading. There's another bit of modern hardware that processes things in parallel. This is SIMD, single instruction, multiple data. With SIMD, it's possible to take a chunk of memory and split it up across different execution units, which are basically like different cores. And then you can have the same bit of code, the same instruction, running across all of these different execution units, but each on its own bit of the data. There's another hardware capability called 64-bit addressing. Memory addresses are just numbers. So if your memory address only has 32 bits, if it's only 32 bits long, you can only have so many memory addresses, about 4 gigabytes. But most modern hardware supports 64-bit addressing, which offers 16 exabytes of memory addresses. So that's a big difference. Adding 64-bit support will take the artificial limitation out of WebAssembly. But these applications don't just need to run fast. Load times need to be fast too. One big step here is to do streaming compilation. So this is where you compile the code while it's being downloaded. And WebAssembly was designed for this. A tiered compiler also helps. Now in Firefox we have 2 compilers. The first one, the baseline compiler, starts when the download of the file starts. Then another compiler, the optimizing compiler, runs on several threads in the background. This one takes longer to compile, but it generates extremely fast code. We're also working on a new optimizing compiler called CraneLift. CraneLift is designed to compile code quickly. It can compile code in parallel at a function-by-function level. But the code it generates is still fast. And we're currently working to see if we can make it generate even faster code than our current optimizing compiler, which is already incredibly fast. There's an even better trick that we can use to skip compiling most of the time, though. So unlike JavaScript, if you load the same WebAssembly file once, twice, 2, 3, 4 more times, it compiles to the same machine code each time. So we can store the compiled code in the HTTP cache. That means that when the page is loading and it goes to fetch the WASM file, the cache will instead give it this pre-compiled machine code. And so that will skip compiling completely. And there are ways to skip even more work, so stay tuned to see what else happens to improve load times. Where are we with supporting these heavyweight applications right now? For the threading, we have a proposal that's pretty much done, but a key piece of that, shared array buffers, had to be turned off in browsers early last year. They will be turned on again soon, though. SIMD is under active development at the moment. For WASM 64, we have a good picture of how this will work, and that is pretty similar to how x86 or ARM got their support for 64-bit addressing. For streaming compilation, we added our streaming compilation to Firefox last year. And in Firefox, we compile the code so fast that it's basically done compiling by the time the file is downloaded. And other browsers are adding streaming too. And Firefox also added a baseline compiler last year. And other browsers have been adding the same kind of architecture over the past year. In Firefox, HTTP caching is very close, and other improvements are still in discussion. Even though this is still all in progress, heavyweight applications are already coming out today because WebAssembly already gives these apps the performance that they need. But once these features are all in place, that's going to be another achievement unlocked, and more of these heavyweight applications will come to the browser. But WebAssembly isn't just for desktop applications. It's also for regular web development, the small modules kind of web development that we're all used to. So if you have a module that does a lot of heavy processing, That's a good use case for WebAssembly. And again, we're already seeing some of this. For example, the parser in the source maps library that's used in Firefox's DevTools and Webpack is now 11 times faster after having been rewritten in Rust compiled to WebAssembly. And the Gutenberg parser in WordPress is now an average of 86 times faster. But for this to go mainstream, we need to have a few more things in place. So first, calls between WebAssembly and JavaScript, they need to be fast. When WebAssembly first came out, these calls weren't fast. That's because engines needed to optimize them. We finished our work on Firefox doing this optimization last summer, and now some of these calls are actually faster than non-inlined JavaScript to JavaScript calls. That brings us to another thing, though. You often have to pass data between your WebAssembly and JavaScript. So for example, you have to pass arguments into your WebAssembly function and return values from it. This can be slow, and it can be difficult too. At the moment, WebAssembly only understands numbers, so that means that you can't pass more complex values like objects into your WebAssembly function as parameters. You need to convert that object into numbers that you can stuff into linear memory and then pass a pointer over to the function. So that's kind of complicated, and it takes some time to actually do that conversion into numbers for linear memory. So we need this to be easier and faster. We also need to integrate with ES modules, because right now you can't use import and export with WASM modules. But that means that the WebAssembly module isn't really part of the JavaScript module graph. Just being able to import and export doesn't get us all the way there, though. We also need ways to distribute and bundle WebAssembly modules. And since these modules shouldn't look any different to the people who are using them, there's no reason to create a separate ecosystem. And there's one more thing. Support for older versions of browsers, even those that don't know what WebAssembly is, like IE11. So where are we on all of this? Well, calls between JavaScript and WebAssembly are fast in Firefox now, and other browsers are also working on this. For easy and fast data exchange, there are a few proposals that will help with this, such as AnyRef, host bindings, and weak refs. And I unfortunately don't have too much time to go into the details on this, but in the meantime, the Rust ecosystem has created tools that handle all of this automatically for Rust code. For ES module integration, the proposal is pretty far along. For toolchain support, tools in the Rust ecosystem can package your code for NPM, and the bundlers are also actively working on support. And finally, for backwards compatibility, there's the WASM2JS tool. And that takes out your WASM file and spits out a JavaScript equivalent of it. Now, this JavaScript is not going to be fast, but at least it will work in older versions of browsers that don't know what WebAssembly is. Once we unlock this achievement, we open the path to another two. Rewriting large parts of JavaScript frameworks in WebAssembly, and making it possible for statically typed compiled to JavaScript languages to compile to WebAssembly instead. So this is languages like Scala.js or Reason or Elm. For both of these use cases, WebAssembly needs to support higher level language features. So first, let's look at rewriting parts of JavaScript frameworks. For a framework like React, you could parallelize virtual DOM diffing with Rust. And you could also speed things up and reduce memory usage by using a different memory allocation scheme. But you'd still need to interact with JavaScript objects, things like the components that users are writing from that code. You can't just rewrite everything and put it in linear memory because that would be difficult and inefficient. So you need to be able to integrate with the browser's built-in garbage collector at the same time. Now this will also help with languages that compile to JavaScript like Scala.js, Reason, or Elm, because those languages use JavaScript's garbage collector when they compile to JS. And that's the same garbage collector that WebAssembly will use when it's running in the browser. So they won't need to change their GC. We also need better support for handling exceptions. And we need good debugging support. Dev tools make it really easy to step through your JS code in the browser. We need the same thing for WebAssembly. And finally, for many functional languages, you need to have support for something called tail calls. So where are we on this? Well, for garbage collection, our team already has a prototype of this working, but it will still be some time before that all goes through standardization. So we're probably looking at sometime next year. Exception handling is still in the research and development phase. For debugging, there's currently some support in browser dev tools, but it's still not ideal. So we're actively working on this, and there's a subgroup of the WebAssembly CG working on specifying it. And the tail calls proposal is also underway. Once those are all in place, we'll have unlocked JS frameworks and many compiled to JS languages. So those are all achievements that we can unlock inside of the browser. But what about outside of the browser? Now, you may be confused when I talk about outside of the browser, because isn't the browser what you use to view the web? And isn't that right in the name, WebAssembly? But the truth is, technologies like HTML, CSS, and JavaScript, they're only part of what makes the web. They're the visible part. They're what you use to create your user interface, so they're the most obvious part of the web. But there's another really important part of the web that has properties which aren't as visible. That is the link. The link's innovation is that I can link to your page without having to put in any central registry or ask you or even know who you are. It's this ease of linking that enabled us to form global communities with people that we don't know. But there are two problems that we haven't addressed with just the link. The first one is, you go visit the site and it delivers some code to you. How does it know what kind of code it should deliver to you? Because if you're running on a Mac, then you need different machine code than somebody running on Windows. Does a website need a different version of the code for every possible device? No. Instead, the site has one version of the code, the source code, and that's what's delivered to the user. And then it's translated to machine code on the user's device. The name for this concept is portability. With it, websites don't need to know what kind of device you're running. But that brings us to the second problem. If you don't know these people whose websites you're going to, how do you know what kind of code they're giving you? It could be trying to take over your system. Doesn't this vision of the web, running code from anybody whose link you follow, mean that you have to blindly trust anyone who's on the web? This is where the other key concept from the web comes in, and that's the security model. Basically, the browser takes that code and puts it into a sandbox, and it puts a couple of toys into the sandbox, things that aren't dangerous, so that the code can do some stuff. But it leaves the dangerous things outside of the sandbox. So the utility of the link is based on these two things: portability, being able to deliver the same code to any device and run it, and the sandbox, the security model that lets you run that code without putting your machine at risk. So what difference does it make if we think about the web this way? Well, it changes the way that you think about WebAssembly. You can think about WebAssembly as just another tool in the browser's toolbox, which it is, but it's not just that. WebAssembly also gives us a way to take these other two capabilities of the web, the portability and the security model, and bring them to other use cases that need them too. We can expand the web past the boundaries of the browser. Now, you may be thinking that already happened with Node.js. But as it is today, Node doesn't quite get us there. It doesn't give us full portability, and it doesn't give us the same security, the same confidence to run this untrusted code either. With Node, it's possible to run JavaScript on servers and other devices without a browser. So that does give us a little bit of portability. But you still need native modules in a lot of cases, either because the native code performs better, or because you already have code written in a language like C or Rust, and you want to reuse that. But native modules aren't portable. When the user is installing your app, the native module needs to be compiled specifically for that device. We're also still missing security. Node could have taken the sandbox from the browser, but Node made the design decision early on that JS modules would have full access to system APIs. So these capabilities, things like direct file access, are the dangerous toys that aren't available in the browser's sandbox. Even though they're dangerous, they do make a certain kind of sense for the use cases that Node was addressing. The thing I want to make clear here, though, is that Node made a choice, and really it's that Node had a choice to make. For JavaScript modules, it could have gone with a sandbox-style approach. So that was the choice it could make. But for native modules, Node had less of a choice, because it's really, really hard to sandbox native code. So Node has already made this choice. If you're running a Node app, you've basically said, I trust this code. Despite this choice, WebAssembly can still help Node. It could eliminate most of the need for native modules, ones that are compiled on the user's device when the user is installing the app for that specific kind of device. These modules could be written in WebAssembly instead and just compiled once by the developer. And then these modules could run across all of the different devices, just like JavaScript modules do. The only problem here is that WebAssembly doesn't have direct access to the system's resources. We need to pass in functions so that these modules could work with the operating system. For Node, this will probably include a lot of the functionality that's in things like libc and POSIX. So POSIX is the Portable Operating System Interface, which is an older standard, and that helps with compatibility. So it provides one API for interacting with the system across a bunch of different Unix-like operating systems. So to make this work, the Node folks would need to figure out what API they want to use for the system interface. But wouldn't it be nice if that were actually something that was standard? Not something that was constrained just to Node, but could actually be used across other runtimes and use cases too. Now what I used to say here was a POSIX for WebAssembly, if you will, a POSIX, a Portable WebAssembly System Interface. And I would talk about how if this system interface were designed in the right way, you could even implement the same API in a different way for the web. So that's what I used to say here. But I don't have to talk about this in what-if terms anymore, because we recently started a subgroup of the W3C WebAssembly community group to standardize this. And we seeded it with a proposal for how this system interface should work. This new system interface is called WASI, the WebAssembly System Interface. WASI won't be part of the WebAssembly spec itself, and there will be WASM hosts, WASM runtimes, that don't make this system interface available, and that's fine. But for those platforms that can make use of the system interface, there will be a unified API for calling these functions, no matter which platform your code is running on. And this will make making universal modules, ones that run across both the web and Node, so much easier. So WASI, it opens up all sorts of use cases for WebAssembly. So that's why I brought Till here, to explain more about that.
So at this point, I used to say that we and others are working on standardizing a system interface for WebAssembly, and that I think we have a pretty good chance. But after seeing the overwhelmingly positive response to the announcement we did a couple of weeks ago, I'll go stronger than that. I think this will succeed, and it'll really change how parts of software development work. Solomon Hykes, one of the co-founders of Docker, tweeted in response to our announcement that if WebAssembly and WASI had been around 10 years ago, they wouldn't have needed to create Docker. And that's obviously a very strong statement. And he backed it up with some more explanation of what he meant by that. I encourage you to look at those tweets. But he ends the tweet with saying he hopes that WASI is up to the task. And I think it is. And I think it's not only up for the task for the domain. Docker is mainly used for containers, for server-side computation, but also in lots of other domains. And I'll talk a bit about some of these different domains. One of them, of course, is the server-side compute, the domain of CDNs, serverless, and edge computing. The Fastly CDN, for example, serves a significant fraction of the internet's traffic. They are moving from serving static files to running their customers' code on every single request. And they're doing this without adding, say, 10 times as many machines to their network, which is really what they would need to do for traditional server architectures. And I'm saying traditional here for something like serverless, where we heard earlier that it really is still not fully mature. But the much lighter weight containers that WebAssembly will enable really change the game here. We are talking about dozens of microseconds of cold startup times instead of hundreds of milliseconds, and running tens of thousands of instances in a single process. So you can really start one of these instances for a request, let it run for a few microseconds, and tear it down again. So WebAssembly gives them the sandboxing they need for their use case at the speed and at the scale that they need. People are also working on building blockchain platforms with WebAssembly. I think at last count we were aware of 10 or so different blockchain platforms being built around WebAssembly virtual machines. And there's interest in the IoT space and in writing portable CLI tools with WebAssembly. We've also seen interest from companies building game engines where WebAssembly can be used as a sandbox for game logic to run in. And with projects like Wasmjet and Nebulet, some people are working on making it run inside operating system kernels. All of these use cases have in common that sandboxing and portability, as Lynne explained, are really important for them. But I want to highlight some additional, less obvious commonalities here. For example, how do things like file access work, or talking to the network? The way to do these things should ideally stay the same across all of these use cases. If you use WebAssembly with JavaScript in the browser or in Node, then JavaScript is used to let WebAssembly talk to the outside world. You use fetch in a browser to load a file from the server. In the browser, all of this is standardized, so you can rely on it. You use Node's fs.read file to read a file from the disk. And you can also rely on that, but for a different reason. There's really only one runtime you would use, Node. Because Node is a de facto standard. So you use the APIs, or so you know the APIs you can use because it's, well, Node's APIs. Ideally, we'll have a similar situation for WebAssembly, where you know what APIs you can use, but not through one runtime being completely dominant. Instead, we are working towards a standardized runtime environment, WASI, which means there'll be a set of functions you can rely on for things like file access or network access. And that means you can compile your code once and run it in all these different environments and in different runtimes that provide these functions that implement WASI. Or also in the browser, where WASI can be implemented in terms of JavaScript using existing DOM APIs like fetch. And in fact, we do have an implementation of the preliminary version of the WASI standard that we put forward. So you can have runtimes that are really tailored towards different use cases instead of needing to rely on a one-size-fits-all solution. And for WASI, we could have said, let's just use POSIX and be done with it. Unfortunately, that eliminates one of WebAssembly's big advantages, the security model, and in particular, the sandboxing. Lynne talked about how Node had a choice to make, at least for JS modules. A choice between keeping the sandbox that JavaScript runs in the browser, or giving it an easy way to talk to the outside world. And we now have the same choice to make, essentially. Do we go with this easiest route, but give up on sandboxing, or do we do something different? Something that enables better control and leads to better security and auditability. That last point is really important. You should be able to see what an application you're about to run can do to your system. And I'm not talking about code review, where you're really looking through, okay, what is this code trying to do? And maybe it's malicious code and really hides well what it tries to do. Instead, you should be able to essentially look at the tin and be able to tell what is the upper limit to how this code could access your computer. With POSIX, that is incredibly hard, and also with other existing system APIs, system interfaces. And it requires support from the operating system. And naturally, it works differently between different operating systems. So there goes your portability. solid, portable sandboxing is just incredibly hard. Back when Node was created, nobody had really figured out how to apply it to the real world. But with things like Google's Fuchsia operating system, this has changed. Better designs exist. And for WASI and our implementation of WASI, WASM-Time, we're working on a standard library design that'll make it easy to build secure, auditable, and portable modules and applications that'll work for all of these different use cases. So with the standardized API with WASI, you can get the same flexibility that you have with Node, but still have security, auditability, and the ability to run code in very different runtimes. And we are also making sure that you can use the tools you're already used to. The debuggers, such as LLDB and GDB, and IDEs such as Xcode and Visual Studio Code, and just without any modifications, without special bespoke tooling, the compilers for languages such as Rust, C, C++, and other languages. Go added support, experimental support for WASI 2 days after we announced the standardization effort. So as you can see, there's a lot of active development in this space. We are all working hard to make sure it is easy to target these use cases and without requiring you all to jump through hoops to compile your code and to debug it. And with this, we bring these capabilities of the web that Lynne mentioned, the portability and the security, and the auditability that I mentioned, to all of these use cases.
Thank you, Tel. So now, let's zoom back out and look at this skill tree. I said in the beginning that people have a misconception about WebAssembly, this idea that the WebAssembly that landed in the MVP was the final version of WebAssembly. I think you can see now why this is a misconception. Yes, the MVP opened up a lot of opportunities. It made it possible to bring a lot of desktop applications to the web. But we still have many use cases to unlock, from heavyweight desktop applications to small modules to JS frameworks and all of those things outside of the browser. Node and serverless and the blockchain, portable CLI tools, and the Internet of Things. So the WebAssembly that we have today, that's not the end of the story, because WebAssembly still has promise to keep and many places to go before it sleeps. I want to thank my collaborators on developing this talk, Luke Wagner and Till Schneidereit, and thank you all for listening.